Hi, I'm Brodie Norfolk, a PhD student at Swinburne University under the supervision of Professor Sarah Madison and Dr. Christoph Pant. In this talk, titled ATCA Reveals Dust Traps at the Edge of Cavities in Transition Disks, I will be summarising the results of my recently submitted paper with the listed co-authors. This includes the results of the Disks Down Under survey, which is an 8.8mm survey of southern transition disks observed with ATCA. If you don't want to listen to the full talk, we conclude that our ATCA and ALMA data shows that both the 8.8mm and sub-millimeter grains share a similar cavity size, suggesting that companions are the main mechanism driving cavity formation in our transition disks. If you want to know how we reached this conclusion, continue to watch. ATCA is an Australian interferometer that is the only array capable of observing under 80 GHz in the Southern Hemisphere. It's comprised of 6 22-metre antennae, and our observations are conducted in the maximum baseline 6-kilometre array configuration. At 7 millimetres, there is a theoretical resolution of 0.3 arcseconds. Here I present results from the Disks Down Under survey. Observing at 33 and 35 GHz bands, we detect 15 out of 16 targets, and the average signal to noise is under 10. Many sources present elongated beams, which is caused by low UV coverage, mainly resulting from flagging due to poor observing conditions. The majority of our disks, outlined in blue, show some form of central deficit of emission, indicative of the presence of a cavity. Now, this is characterized in our ATCA observations as 2 peaks of emission. The aim of this research is to 1, explore the grain size distribution in transition disks, 2, understand grain evolution and dynamics in these disks, and 3, investigate the origins of cavities in TDs. These questions can only be answered by probing different populations of grain sizes, which require a multi-wavelength comparison. However, given the comparably poor spatial resolution of our ATCA continuum maps, as seen below for HD 100-453, we choose to conduct our comparison in the visibility space. This figure shows in columns 1 and 3 the ATCA and ALMA visibilities and models, and in columns 2 and 4 the reconstructed 1D radial brightness profiles. We present our ATCA observations with blue and our ALMA observations with red. We also restrict our analysis to sources with ATCA observations above 5 sigma. This leaves us with 10 disks. For the majority of our sources, the visibilities for both ATCA and ALMA data cross the null, that is the y=0 line, at the same point. This is indicative of a similar cavity size between the grain populations probed by ATCA and ALMA. In order to quantify this, we modeled our data using Frankenstein. Frankenstein uses a Gaussian process to reconstruct the 1D radial brightness profile of a disk non-parametrically. We utilize a azimuthally symmetric brightness profile despite known asymmetries in our sample, as we are solely interested in obtaining a cavity radius. Our 1D radial brightness models support our previous claim that the majority of our sample share a similar cavity radius shown by the brightness peak of the ATCA and ALMA 1D radial profiles. Now, plotting this radial peak position, that is our peak values, we see that the majority of our sample, in pink, all follow a 1-to-1 correlation. By adding other transition disks from the literature, shown in blue, we also see that the majority of these targets follow the correlation. This suggests that for these sources, both the small grains probed by ALMA and the big grains probed by ATCA share a similar radial distribution. However, from our sample, HB char and J1608, and from Vanderplas 2017, HD 97048, fail to show a cavity at 34 GHz and don't follow this trend. The question now is why? At 34 GHz, there's other sources of emission that could be obscuring the presence of a cavity. At 34 GHz, thermal free-free emission originating from ionized gas can cause the integrated flux to vary from 20 to 40% over a period of days, weeks, or years, whereas non-thermal synchrotron emission originating from electrons spiraling in a magnetic field can cause the integrated flux to double over seconds, minutes, or hours. Given the variability of each source of emission, temporal flux monitoring is required. However, a quick test is to look at the spectral slope. Disks containing other sources of emission will exhibit an integrated flux above that expected from thermal dust, which is represented by the red line. For our sample, only SC char and RY loop exhibit emission above that assumed from thermal dust. But this is within 40% and is likely due to thermal free-free emission. But again, temporal flux monitoring is required to confirm this. For our three sources that don't follow the one-to-one correlation, HB char doesn't appear to exhibit any excess of emission. J1608 is excluded due to insufficient known millimeter fluxes, and for HT 97048, Van der Plas 2017 is actually able to prove thermal free-free emission is likely present using a spectral slope. Another explanation for HB char and J1608 is that these sources are showing strong asymmetrical emission that is typically seen at longer wavelengths. Asymmetries appear to be linked to local low gas surface density in concentrated regions of large grains. This has been seen previously for HDEN 142527 in Cassius 2015. In a multi-wavelength continuum map seen in the right, there's a strong concentration of 34 gigahertz emission within the 700 and 345 emission. Local gas pressure bumps can be induced by gas horseshoes due to highly eccentric binary companions, Rossby wave instabilities at the edge of planet-carved gaps, or spiral density waves launched by a companion. If we again look at our continuum maps in the two panels below, J1608 is strongly asymmetric at 8.8 millimeters, and it's likely that due to the azimuthal symmetrical assumptions in the Frankenstein code, the model is unlikely to recover a deficit of central emission in the 1D radial brightness profile. And for HB char, the source was too faint for Gaia to measure proper motions, and as a result, we could not confidently phase center the disk. So it may or may not be asymmetrical. Now let's return to our sources that follow the one-to-one correlation. What physical mechanism can cause a shared cavity size between both small and large grains? Well, historically, grain growth due to the vertical settling, radial drift, and coagulation has been proposed to dominate grain evolution in disks. This will result in a radial and vertical size sorting and growth to sizes outside current observational capabilities. The visibilities are expected to resemble that of TW Hydra, presented in Andrews 2015 in the right panel. Observations at longer wavelengths probing larger grains will either cross the null further along the x-axis or not cross at all. However, none of our sample exhibits these features. Another possible explanation is the dust trap. The trapping of dust at local maxima in the gas density. Dust grains interior to this maximum will accrete onto the host star and a cavity will form. Several mechanisms can produce dust traps. Let's start with photoevaporation. As accretion onto the host star decreases, high energy photons can further impinge the accretion flow and photoevaporate the disk further away. This limits the resupply of inner disk material and increases the local gas pressure at the photoevaporation front, trapping dust at the inner edge of the disk. Models by Ercolano and Pescucci predict that disks dominated by photoevaporation will have relatively small cavities and low accretion. None of our sample fits this criteria. Next, in regions of low ionization, where the magnetorotational instability is inhibited, there is an increase of accretion stress and subsequent local maxima in the gas pressure that can trap dust. However, models by Pinilla, based on dust trapping at dead zone edges, are required to have a relatively large turbulence of alpha equal to approximately 10 to the negative 2. Whereas observations of typical protoplanetary disks by Panta and Flaherty and models of transition disks by Dong and Toki suggest that an alpha between 10 to the negative 3 and 10 to the negative 4 are more suitable. These dead zone models also require a factor of 2 between the sub-millimeter and millimeter radial brightness peak, which again is not supported by the one-to-one correlation we see from our observations. Lastly, dust traps can result from the dynamical clearing by a companion. The formation of an interior planetary mass companion will locally deplete the gas and/or dust in the disk and produce a pressure bump at the cavity edge, as seen for HD 100453 in Nealon 2020. While the tidal truncation of the disk by a binary companion results in a gas pressure bump at the leading edge of the truncation, as seen for HD 142527 in Price 2018. Other models, including a 10 to 15 Jupiter mass companion in Pinilla, also suggest a similar radial peak value for submillimeter and millimeter grains. Our data appears to suggest that although it's likely that these mechanisms can occur simultaneously in disks, the presence of a companion is dominating the grain evolution of our sources, following the one-to-one correlation. Now, if we revisit our science questions, firstly, exploring the grain size distribution in transition disks. Well, our visibilities in Frankenstein 1D radial brightness profiles reveal that both the large grains and the small grains in most of the disks share a similar cavity size and radial position. 2, understanding grain evolution and dynamics in these disks. Well, it's likely that if a companion is present, it will dominate the evolution of the disk. And 3, investigating the origins of cavities in transition disks. Well, for our sample, the only plausible explanation for both grain populations to share a similar cavity size and radial position is that the formation of the cavities are driven by the presence of a companion. And we conclude that large cavities in transition disks will likely result from a dust trap,